Today we're going to look at the inverse hyperbolic functions. And so remember, inverse functions are found by inverting or switching our x's and our y's, our domain and our range. So I'm just going to list the domain and the range of our inverse hyperbolic functions based on the graphs of those hyperbolic functions that we've learned previously. Here is the domain and the range of the inverse hyperbolic sine function, and the domain and range of the inverse hyperbolic cosine function, the inverse hyperbolic tangent function, and the inverse hyperbolic cosecant function, and the inverse hyperbolic secant function, and the domain and range of the inverse cotangent, hyperbolic cotangent function. Okay, let's go to Desmos and look at the graphs of these inverse hyperbolic functions, and so you can be familiar with these. So here's the inverse hyperbolic sine function, the inverse hyperbolic cosine function, the inverse hyperbolic tangent, the inverse hyperbolic cosecant, inverse hyperbolic secant, and the inverse hyperbolic cotangent. As you can see, I quickly went through those graphs. I'm not going to require you to memorize those graphs in this class, just to give you the basic idea, knowing the restrictions of the domain and range. That's the main thing that needs to help you in this. Okay, next we're going to look at finding the derivative of inverse functions, and there's a number of formulas to memorize. I'm going to walk you through how the inverse of the hyperbolic sine function's derivative is developed, and I'm going to use implicit differentiation to show you how the formula is applied. So basically, first thing we're going to do is, since this is an inverse, we're going to switch our x's and y's and switch it from inverse hyperbolic sine to just the hyperbolic sine. So that's the definition of inverse functions. Now I'm going to take the derivative of the left-hand side and the derivative of the right-hand side with respect to x. So when I take the derivative of the hyperbolic sine of y, that gives us the hyperbolic cosine of y times dy dx, because we're with respect to the x variable. Y is some function of x. On the right-hand side, our derivative is just simply 1, so we can get dy dx is equal to 1 divided by the hyperbolic cosine of y. But we're not done. Now this is where we're going to use those identities that we had at the beginning of our section on hyperbolics, and I'm going to solve this for the hyperbolic cosine function. So first I'm going to get the hyperbolic cosine squared by itself, and then I'm going to square root each side. And so I'm going to go back to my derivative, replace the hyperbolic cosine with the square root of 1 plus the hyperbolic sine squared. Still not done, because I know the hyperbolic sine of y is equal to x. We define that up here at the very top. So I'm going to replace that with x. So I have my derivative is equal to 1 over the square root of 1 plus x squared. That is our formula for the derivative of the inverse of the hyperbolic sine. And then I'm going to just give you the other ones. You can go through the process if you want to find them. So here is our derivative of the inverse of the hyperbolic sine function of u with respect to x. So I'm using the chain rule here. Here's the derivative of the inverse of the hyperbolic cosine function. The derivative of the inverse of the hyperbolic tangent function, the derivative of the inverse of the hyperbolic cosecant, next we have the derivative of the inverse of the hyperbolic secant, and last but not least, the derivative of the inverse of the hyperbolic cotangent. Now, what do you notice about the last two? We notice that the derivative of the inverse of the hyperbolic tangent and the derivative of the inverse of the hyperbolic cotangent function are the same answer. So if we're going the other direction, we're trying to integrate, and we find the integral of u prime over 1 minus u squared, we got to figure out, should we write the inverse of the hyperbolic tangent or the inverse of the hyperbolic cotangent? Well, to do this, so when we integrate, we will need to select the proper antiderivative. How do we decide which is the proper antiderivative? That is based on the domain of x. So you need to figure out, when I'm taking the integral, is my answer going to be equal to the inverse of the hyperbolic tangent, or is it going to be equal to the inverse of the hyperbolic cotangent? There are two ways for you to do this. Our first method is to look at the domain and range from that table I gave you at the beginning of this video. The second way to do this is to look at this restrictions I'll give you for the last blank here when we take the integral of 1 over a squared minus u squared. So either way, whichever way is easier for you to remember, that's how you would figure out, is it going to be the inverse hyperbolic tangent or the inverse hyperbolic cotangent. But before we do that, let's first go over the integrals that will result in the inverse hyperbolic functions. Our first one is the integral from 1 divided by the square root of 1 plus u squared du. When I see that pattern, I know my answer is equal to the inverse of the hyperbolic sine of u plus c. Next, I'm going to find the integral of 1 over the square root of u squared minus 1. So this time I have the square, in the denominator I have the square root of u squared minus 1 is our pattern. That is equal to the inverse of the hyperbolic cosine of u plus c. Next, I'm going to look at the integral of 1 over a squared minus u squared. So 1 over a number squared minus a variable squared. Okay, when I see that pattern, it's either going to be the inverse of the hyperbolic tangent or the inverse of the hyperbolic cotangent. And this is how you figure out which is which. Your answer will be the inverse of the hyperbolic tangent function of u plus c if the absolute value of u is less than 1. And it will be the inverse of the hyperbolic cotangent of u plus c if the absolute value of u is greater than 1. Okay, if I see the pattern, the integral of 1 over u, the square root of 1 plus u squared du, will be equal to negative the inverse of the hyperbolic cosecant of u plus c. If I see the integral of 1 over u, the square root of 1 minus u squared du, then I know that integral is equal to negative the inverse of the hyperbolic secant of the absolute value of u plus c. Okay, so let's do some practice problems. Okay, my first example, number 5 here, is I'm going to find the derivative with respect to x of the inverse hyperbolic sine of x over 2. So notice I have a function inside my inverse hyperbolic function, which is x over 2. So that's going to be my u. So if u is going to be equal to x over 2, the derivative of that is 1/2. Because remember, you take what our derivative is equal to and you times it by u. So I'm going to plug that into my function, but I'm going to times by the derivative of u. And when I times by the derivative of u, I'm going to multiply by 1/2. So instead of writing that separate, I'm just going to write that in the front as 1 over 2. So you see a 2 on the denominator. That's because of multiplying by my derivative. So using my formula, I know that's equal to 1 over the square root of 1 plus my u squared, and then times by du, which gives us that 1/2 in front. Okay, so we found the derivative, but now we need to simplify our answer. So I'm going to start by distributing that square to the x and to the 2 to rewrite my function as 1 divided by 2, the square root of 1 plus x squared over 4. I still need to do some simplifying. I don't want to have a fraction underneath the radical if I can get rid of it. And so since 4 is a perfect square, I'm going to rewrite that what's underneath the radical. I'm going to rewrite 1 as 4 over 4. And so I got 4 over 4 plus x squared over 4. Adding my like terms, that gives me 4 plus x squared over 4. And then if I take the square root of the top and the square root of the bottom, we're looking at the bottom, the square root of 4 is 2. So I got 2 in the denominator and 2 in the numerator of that fraction on the bottom. And so I therefore can simplify those 2's out and write my final answer, my final simplified answer, 1 divided by the square root of 4 plus x squared. Okay, now let's look at number 6. Here I'm going to find the derivative with respect to x of the inverse hyperbolic tangent of x quantity squared. So since the inverse hyperbolic tangent function's inside the square operation, I'm going to have to find this derivative using the chain rule. So I'm going to start by taking the derivative of the outside, the derivative of a square operation. That will give me 2 times, and I'm going to copy down the derivative of the inside, copy down the inside function. So that's 2 times the inverse hyperbolic tangent of x. Knowing our chain rule, I need to multiply this by the derivative of the inverse hyperbolic tangent function. Well, we know that from our formulas to be equal to 1 divided by 1 minus x squared. So now I'm just going to put this together and write this as 2 the inverse hyperbolic tangent of x over 1 minus x squared. Now let's do some integral practice. Our first integral problem is I'm taking the integral of 1 minus the square root of 4x squared minus 2. Now, as it's written, unfortunately, this does not meet any of our formulas. But the first thing I notice is 4x squared can be written as 2x quantity squared. And so I'm going to make u 2x, not the 4, not 4x. I'm going to make my u my 2x. I need to figure out what the derivative of 2x is. And the derivative of 2x is 2. And so I can replace the dx with du over 2. So that's what I'm going to do. The integral of 1 over the square root of u squared minus 1 times the derivative of u over 2. So now what I'm going to do is I'm going to factor out that 1/2, factor out my constant, and rewrite this integral as 1/2 the integral of 1 over the square root of u squared minus 1 du. Now I recognize that the integral of 1 over the square root of u squared minus 1 is equal to the inverse hyperbolic cosine function. So I result in 1/2 the inverse hyperbolic cosine of u plus c. In the last step, always go back to original variable. So I'm going to replace the u with 2x, and that's my integral of this problem. Okay, we're going to do a similar process for number 8 here. So we're going to find the integral of 1 divided by 2x, the square root of 1 minus 9x squared. So the first thing I notice is that 9x squared can be rewritten as 3x quantity squared. So I'm going to make u equal to 3x. So derivative of u would be equal to 3 dx. So I can replace dx with 3 divided by, du divided by 3. So that's equal to the integral of 1 over 2x, the square root of 1 minus u squared du over 3. I still have a problem. This does not equal the form. It's close to 1 over u, the square root of 1 minus u squared, that integral. So I need to get u in front of that square root symbol, and u, remember, is 3x. I need a 3x. Then I remember that if I multiply 2x times 3, that's the same as multiplying 3x times 2. So I'm going to switch my 2 and my 3. 1/2 the integral of 1 over 3x, the square root of 1 minus u squared du, and then I can replace that 3x with u, and I finally have our formula. So I have the integral of 1 over u, the square root of 1 minus u squared. So I recall that is equal to negative the inverse hyperbolic secant function of the absolute value of u. So that means I have negative 1/2 the inverse hyperbolic secant function of the absolute value of u plus c, and of course replacing my u with 3x.